The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone, I welcome the viewers of another episode of my video series on the Earth System. This video is about the principle of isostasy. This is one of the most important basic principles that should be understood when dealing with plate tectonics and geodynamic movements. We assume that the lithosphere is in equilibrium with the underlying asthenosphere. And through plate tectonic movements, but also other external influences, as we will see, this balance is sometimes disturbed so that compensatory movements occur, which ultimately help shape the Earth's surface. This is then called isostatic compensation. And as with all other videos, I would like to point out the opportunity giving me feedback if you have any questions or comments. You will find my email address on the first page of this video or on the website. Let's take a look at this principle using a very simple model. We all know that wood floats in water because it is a little lighter than water. It's less dense. And the amount of water displaced by the block of wood corresponds exactly to the weight of the entire block of wood. Archimedes already knew this, who thus discovered the specific weight or density of materials. When such a block of wood floats in water, it is in equilibrium. The water displaced by the block of wood has the same weight as the entire block of wood, including the part that protrudes above the surface of the water. And now it gets interesting for us. If we stack a second wooden block of the same size on top of the first and immerse them both together in the water, the picture changes. The larger block of wood sticks out higher, but is also deeper in the water. And this block of wood is then also in balance with the water. The first wooden block is 6 centimeters thick and protrudes 1 centimeter from the water. Correspondingly, it is immersed by 5 centimeters. Stacked on top of each other, 2 blocks are immersed in the water by 10 centimeters and protrude 2 centimeters. This reflects the isostatic compensation because the balance is restored by a deeper immersion and at the same time a higher protrusion. The up and down movement required for this is isostatic compensation. Here in the water and wooden block model, the movement naturally occurs very quickly because water flows very easily and can be displaced rapidly. However, for the balance between the lithosphere and asthenosphere, we need geological periods of time. That means 10,000s to millions of years. Let's take a look at this a little more theoretically. We consider the weight which lies upon a compensation surface at a certain point or a small area that is the base of one of these columns. These columns show the 3 situations seen in the model: water alone, the thin wooden block 6 centimeters thick, and the water remaining underneath, and correspondingly the 12 centimeters thick wooden block with the water underneath. All 3 columns have the same weight, although they are different in height, which of course has to do with their density. And they all exert the same pressure on the compensation surface, which we assume in this model to be at the bottom of the water tank. Now let's transfer the wooden block model to the lithosphere and asthenosphere. We assume that the asthenosphere is a flowable mass, so we can view it analogously to water in the wooden block model. The 2 blocks shown here in different colors represent the 2 different types of Earth crust, continental and oceanic crust, each of which has different densities. The density of the flowable asthenosphere is greater than that of the blocks of lithosphere. That is the entirety of lithospheric mantle and crust, continental or oceanic. So this corresponds to the water wooden block model. The density of a material is expressed with the Greek letter rho, which is what here looks similar to a P. I left out specific numbers for now because it's about the principle. I will come back to this in the next video. Oceanic crust, shown here on the right, is generally heavier than continental crust. It is important that this system is in balance. In this case, the same pressure prevails everywhere on the isostatic compensation level, which is this gray colored plane here in this figure. We can imagine this in the same way as with the water wooden block model. A column above the compensation level must have the same weight everywhere, no matter how high it is and what it is composed of, because then it exerts the same pressure at all points of the compensation level. No matter where I place the column, whether it is in the area of the oceanic crust or in the continental crust, the columns, even if they are of different heights, they would all be of the same weight and would therefore exert the same pressure at all points. By the way, it doesn't matter where the compensation level is in the flowable mass. I could also set it lower or higher. Equilibrium would exist everywhere because the fluid mass compensates for changes. But therefore, the compensation level cannot be in the rigid areas that are not flowable, because then compensation could not happen. The principle of isostasy was already described in the 19th century because it was used to explain the different heights of landscapes on Earth, especially the difference between high mountains and plains. There is the principle developed by John Pratt, who assumed that continental crust has different densities, but they all belong to the same plane compensation level, the isostatic compensation level, as explained earlier. At about the same time, George Airy, who on the other hand assumed that the continental crust has the same density everywhere, and therefore, let's think of the water wooden block model, it immerses into the mantle to different depths. Well, we know now that it is basically a combination of both. We have different densities in different types of crust, but we have also different depth of immersion depending on whether it is mountainous or balanced old continental crust. Here in this illustration, only the continental crust is shown, as it was then depicted by Felix Wenning-Meines at the beginning of the 20th century. The oceans are still missing because there was simply no reliable data on them at the beginning of the 20th century. This model was created from all of these considerations and using all data available today. It has everything that is known from geophysical studies, for example about the lower limit of the lithosphere. The lithospheric mantle has exactly the same material composition as the asthenosphere, which represents the uppermost mantle. It is therefore a bit of a contentious point whether the lithospheric mantle should be counted as part of the solid shell of the Earth, the lithosphere, or as part of the mantle. Because it is solid, it reacts in a similar way to the Earth's crust, and because of its solidity, it plays a major role in plate tectonic movements, which is why I think it makes more sense to place it in the lithosphere and not in the upper mantle, even though it has the same material structure. The only difference between the lithospheric mantle and the asthenosphere is that the asthenosphere contains a small amount of molten material, not much. It is thought to be around 2 to 5% at the lower limit of the lithosphere, but still enough to make it flowable. And with this, we have met the conditions for an isostatic balance of the lithosphere, so that, as in our wooden block model, the asthenosphere can flow or escape, just like water, only extremely much slower. The lithosphere is solid throughout and not as hot as the asthenosphere. This in turn has the consequence that the asthenosphere is slightly less dense than the lithosphere. And with this phenomenon, we can then explain some plate tectonic features. For instance, the sinking of the oceanic lithosphere with increasing age. I will discuss this phenomenon in detail in a later video. Finally, it remains to be noted that the principle of isostasy is a very important basic principle for plate tectonics. In the next video, I will show how the resulting isostatic compensation works and in fact can be observed, and what amounts of isostatic movement we have to expect. This time, thank you for listening, and I'll be happy if you stick around. I recommend continuing with the video on isostatic compensation.